Welcome to the fifth lecture in linear algebra series. In previous lectures, we had discussed a system of linear equations can be written in a matrix form Ax equal to B, where A is a coefficient matrix and X is a variable vector and B is a constant vector. And those system of linear equations can be solved by using a Gaussian elimination where you are going to consider an augmented matrix A, B, and then it transformed into an upper triangular matrix, and then we use a back substitution to get the solution for X. Now, there might be a case where you might have multiple system of linear equations with the same coefficient matrix, but with a different constant vector. In those cases also, Gaussian elimination required you to compute again and again. So instead, if we originally perform some operations on A, or if we simplify A, or if we factor A into some matrices, we can avoid those recomputations. That is the main goal in this lecture. That is, we call it as a LU decomposition. That is, we just factor the matrix into two different matrices. So that is what we call it as a matrix decomposition. Matrix decomposition or factorization is the process of breaking down a matrix into product of other matrices. So here we are going to factor A into two matrices, L and U, where L is a lower triangular matrix and U is an upper triangular matrix, and which is very useful in solving system of linear equations and finding inverse. So LU decomposition is, as we discussed, it is a method of factoring a matrix into two matrices where L is lower triangular matrix and U is an upper triangular matrix. Now, how are we going to do that? So we consider Ax equal to B, and in place of A, we consider LU. So LU equal to X, and you consider this Ux as some Y. So and then first we have to solve Ly equal to B, which is an intermediate vector Y, which we solve by using a forward substitution. And you have Ux equal to Y, and we can find the final vector by using a back substitution. So it is similar to, we convert this augmented matrix into an upper triangular matrix. So this is a two-step process which is much faster than the standard Gaussian elimination method, which is for finding a repeated solutions when you have same coefficient matrix. Now, how are we going to find this LU? Now, this, as we said, U is simply that upper triangular matrix that you got after the Gaussian elimination. The lower triangular matrix is, as you know, that the lower triangular matrix is a multipliers used in the elimination process. As we know, one of the elementary row operations that we do to convert that augmented matrix into an upper triangular matrix is adding multiples of one row to another. Now, whatever the multipliers that we have used there, we will be considering as an element of the lower triangular matrix. Suppose you take, as we know, to convert into a row echelon form, first we consider the main diagonal elements as the pivot elements. Suppose if you consider the first row first element as the pivot, and to get zeros in all the elements below, suppose if you consider the second row first element, if you want to make 0, then we will be doing this operation, that is adding multiples of R1 to R2. That is, if you perform R2 as R2 minus MR1, then M we say it as a multiplier that will become an element of a lower triangular matrix, that is L21. So let us consider an example to understand. So suppose we want to decompose this matrix 2, 1, 4, 5. So first we consider this 2 as a pivot, and then we have to make this 4 as 0. To make 4 as 0, we have to perform an elementary operation, that is multiply row 1 element and subtract from the row 2 elements, that is 4 minus 2 into 2, that is R2 as R2 minus 2R1. This 2 we call it as a multiplier. Now the main diagonal elements of L, we consider it as ones, and as it is a lower triangular matrix, all the elements above the diagonal are zeros. So we have to find the elements which are below the main diagonal. There is only one element here, that is the multiplier that we had used. The multiplier that we had used here is 2, so that it will be 2. And after this transformation, we are going to get an upper triangular matrix. All the elements below that main diagonal are 0. So whatever the upper triangular matrix that we got, that is U. So now this is what your LU. You can verify by taking product of LU. When you take the product of LU, we are going to get the same matrix A. So now A is decomposed into LU, where L is 1021 and U is 2103. Now we can check one more example on the 3 by 3 matrix. So here we consider first pivot element as 2. All the elements below that we have to make it as 0. That means we have to make 4 and 8 as 0. To make 4 and 8 as 0, which multiplier that I had to use? 4 minus 2 into 2, 8 minus 4 into 2. So those will be your multipliers. 2 and 4 are multipliers. And once you do that operation, this is the matrix that you are going to get: 2 1 1 0 1 1 0 3 5, and you consider the second row second element as the pivot element, that is 1 here, and again you need to make all the elements below that main diagonal 0. So to make that, we have to consider the multiplier 3, and then we have to perform an operation R3 equal to R3 minus 3R2. So we are going to get this upper triangular matrix. Now what is the lower triangular matrix? We have to see what multiplier that we had used: 2 4 3. To transform second row, we had used the multiplier 2. So the second row first element will be 2, third row first element will be 4, and the third row second element will be 3. That I am talking about the lower triangular matrix. So the lower triangular elements 2 4 3. All the elements above that main diagonal are 0. So this is the L that we got, and we are going to get U as whatever the upper triangular matrix that we got after the transformation. This is how one can decompose matrix A into two components, L and U. Now, so LU decomposition exists only if the leading principal minors of all are non-zero. And as we had seen that if same coefficient matrix is there, we don't need to do the multiple computations of Gaussian elimination again and again, as it requires order of n cube time. Once it is decomposed, by using this equation Ly equal to b and ux equal to y, you can solve for x easily with an order of n square time. Now, as we know, one of the fact is adding multiples of one row to another won't change the determinant value. Now, that is the operation that we are doing when we are decomposing into LU. So the determinant is not going to change. So the determinant of A is determinant of L into determinant of U, and as we know that the determinant of L is 1 because all the main diagonal elements are 1 of L, and determinant of U is simply the multiplication of all the main diagonal elements, that is U11, U22, so on, UNN. And if LU decomposition exists where the diagonal elements are 1, the decomposition is unique. And we had seen that this can be used to solve solve system of linear equations where you have the same coefficient matrix efficiently. Thank you.